Hello, my name is Fabrizio Nunnari. I am a researcher at the German Research Center for Artificial Intelligence in Saarbrücken, Germany. And in this video, I want to show you what is the MMS Player, a software able to convert description format of sign language into animated avatars, animated virtual interpreters. So this is the website. It's an open source software. Here in this diagram, I quickly depicted the input of the MMS Player is an MMS instance, which I'm going to explain you in this video. Is a new annotation system consisting of glosses plus more timing information and inflection parameters. And the MMS Player is based on a vocabulary, a repository of single sign, and it is able to do a composition of single signs into a single timeline. It is based on the Blender software, so the composition of the signs ends up in a Blender timeline, and once it is in Blender, it can be exported as a video, as animation data in several formats, or you can simply go to check your Blender scene and use it the way you like, also to export animations for real-time software like Unity and Unreal and so on. So a disclaimer first. I want to tell you this is a research prototype. It's not a complete working system ready for production. It is missing some key features, and the most important is the face is not animated yet. But I can show you. I can start to show you an example. The example is based on a German dataset of a railway announcement. There is a sentence that in English is translated to information on the trains in direction of Fulda. Fulda is a city in Germany. The trains today are running 15 minutes late, and the reason is that there is an emergency on the track. So I will run the software. Here I have set already a couple of environment variables. You needed to set the environment variables to the Blender software. We use a version 4.2.2, and another variable is pointing to the repository of signs. And if I run the software with this command line says that Blender has to run in background mode, so we'll not open the GUI, execute the main script of the MMS Player, a reference to the generated directory of the corpus containing the single signs. This is the MMS file that is going to be generated, and the result will be exported into this video. And to save time, I'm going to render in only 20% of the size, because the default is HD resolution. So before rendering, I show you here what I'm going to render. This is an MMS. So several columns is a table. You can save it in CSV format, edit with programs like Excel. The first column contains what is normally referred as a glosses, or better in this case, a gloss ID. So each of these names refers to animation data, a small video clip or an animation clip of less than 1 second, playing back a single sign. So this is the sequence of signs that is going to play back. In addition to the gloss information, there are columns expliciting what is the time playback of these signs. You can explicit the timing in absolute values. So from when to when playback this gloss, and if this time is shorter or longer than the nominal playback time of this gloss, the playback will be accelerated or slowed down. For example, if to perform the sign information in the dictionary, it takes 0.3 seconds, but you want to play back it in 0.2 seconds, so the software will accelerate the playback. Time can be explicited in absolute values on the timeline or in relative values. So you specify the transition time with respect to the previous gloss and the duration of this gloss. So this format, the two formats can be used alternatively. In this table, they are both a field, but they are kind of equivalent. In some cases, like when converting from an annotation information, this format is more handy, straightforward. But when you are editing examples manually to do testing, maybe this format is more useful. In addition, there are two columns that are not implemented yet, which would allow you to play back in parallel a different gloss on the dominant and non-dominant arm. This is a work in progress. Plus the remaining columns, skipping this annotation data, the remaining columns, you will see a lot of numbers, and these are inflection parameters. And I will give you an explanation one by one, some examples of what are these numbers and what are the inflection parameters. Consider that all these numbers have been computed automatically in this case, but in the examples that I will show you, I was inserting these numbers manually. So if I run the rendering procedure, the software will start by reading from the dictionary every single sign one by one, apply to each of them the inflection parameters to transform the animation of a single sign into something else, and then scale the duration, the playback speed of each gloss and put it in the final timeline. Now the software is working, and it will take some time to compose the timeline that will end up, in this case, it's something more than 1,400 frames, and we are working with 60 frames per second. So now it's just a matter of waiting. Okay, it has rendered 1,536 frames, and if I go to my file system, this is the file just generated. I open it, you see I play back the German Sign Language version of this sentence. Of course, the resolution is low because I wanted to save time on the rendering. But if you want to debug and see how this sentence was generated, you can take the previous command line. You can remove the options to export the video and resize, and you can also remove the background option. So Blender will open the GUI, and in this case, it will only compose the timeline and open the GUI without rendering the video. And I can show you the content of the Blender scene. Okay, so now this is the resulting Blender scene. If I click space, you can see it is playing back in 3D mode. If I enable the visualization of the skeleton, I go to pose mode and I select one bone. You can see here on the timeline the composition of the sentence from here. And actually, every time there is a sequence of a sign from the vocabulary, it is a dense set of keyframes because it is motion capture data. And every time we do the transition from one sign to the other, you can see there are no keyframes. This is the default transition routine from Blender. So in this way, you can debug what is the result, and as you have the Blender scene, obviously you can export a video or whatever you need, apply changes to the character, transfer the animation to another character, and so on. Now I close here without saving, and I show you some more information on what is an MMS, what you can do with an MMS. I show you this example of duration. So this is a small example repeating the sign index, but with different speeds. And here you can see that you can specify the duration as 100%, so the sign for index is played back in its normal speed, or you can play it to about 1/3 of its speed, or 3 times slower. And then some other examples are specifying the duration in seconds instead of with the percentage. And I already prepared all these videos And here is what you get. 1, 2, 3 times, 1, 2, 3 times is the same sign for index, repeated at a different speed. In addition, you have also the possibility to specify the hold keyword. So holding is a known phenomenon in sign language. So you can make a sign and then hold it for a moment. And in this example, you have index, you hold it, you repeat it 2 times, and you hold, and then you repeat it 3 times. And here is the video resulting from these MMS. 1, 2 times, and 3 times. And as you can see, there is clearly a pause in between the 3 sets of repetitions. Next, I show you the hand relocation and the rotation example. So we have the index sign repeated 9 times. So the name of the file is hand reloc and rotation. If I open this, close the old one, here you see there is the index repeated 9 times with the same duration, with the same transition in between signs, but there are additional columns saying that this sign has to be relocated. So the relocation of a sign consists in taking every point of the trajectory of a hand and moving it in space, rotating or scaling it. In this case, we are executing the index the first 3 times by relocating up on the vertical axis. And also we apply a relocation to perform the sign left and right. 3 times on the original position and 3 times below the original position. And you will see the results. So the rest of the values of the relocation are identity. There is no rotation and no scaling of the trajectory. But there are some numbers in the rotation of the hand. So at the same time, we have the dominant hand that is relocated in space, and the wrist of the hand will be rotated of a certain amount. And now I will play back the video and you will see more clearly what I'm talking about. So this is the index sign repeated 9 times, as it is 9 rows in the MMS. And each time there is a relocation of the trajectory in space and also a rotation of the wrist. So the relocation of the trajectory consists of taking all the points composing the motion of the hand in space, and all these points go through a 3D rigid transformation that is rotating, scaling, and translating all these points at once. Next example, something more complex. The sign not, nicht, repeated 3 times. But the idea is that I say no in 3 different ways. The first time is the original one, and then I use other inflection parameters, like relocation of the torso, relocation of the hands, and also I inflect the rotation of the head. So I operate on the joint of the neck, and also the same inflections of the dominant and non-dominant hand, because the sign is performed with two hands. And what I simulate is that the sign not is said the first time normal, the second time is like whispering at the camera, and the third time is exaggerated. So again, 3 times. Now I go through it frame by frame. The normal version is as it is recorded in the dictionary. The second time, the torso leans forwards, the head goes back a bit, and the trajectory of the hands is scaled horizontally to shrink it and keep it more closer to the center between the two hands. And the third time, the torso goes back, the neck rotates the head forward, and the trajectory of the hands is scaled with a factor higher than 1 to exaggerate the trajectory and make the sign bigger than the original. So essentially, this is the same original motion capture data for the sign nicht, not. But thanks to the inflection capabilities, we are able to perform runtime editing on the full body of the character in order to give different meaning or different flavors to the execution of a sign and better adapt it to the context of the sentence. So next I wanted to show you an example for the sentence we saw before in a collage where you see at the same time the original motion capture data of the sentence, then the inflected version, and then the non-inflected version. I play it back. Okay, so what you see on the right side is essentially the concatenation of the single signs, while in the middle you see the software can mimic more closely what is the original recording of the sentence, because this middle animation is generated by applying inflection parameters to the data of the single animation clips of the single signs. For example, here you can see that the original sign is performed lower, but the inflected version is a bit higher, which is matching a bit more the position of the hands in the sentence. And also the head is a bit more straight than the version in the vocabulary. Here you can also see the position is higher with respect to the sign recorded. Here you can see that in the sign recording the hand is down, but here we were able to inflect the position of the hand and match the position that we see in the sentence. And also the inclination of the head matches better what is the inclination and the position of the head of the single sign. Here another example. The original sign for minute is performed using the joining the finger tips and hitting the other hand, but during the performance of the sentence, our interpreter used a variant that is touching the face rather than the other hand, and just thanks to the inflection capabilities, we were able to adjust the execution of this sign and match one of the sentence. This goes even beyond the intended version of the inflections, but in this case it worked pretty well. So now to the conclusions. This is, as we said, a working prototype. There is a lot of work still going on, research work. We are working on including facial animation, that at the moment the face is not animated at all. There is already existing experimental code to support parallel signing, so that you can perform in parallel, for example, 3 glosses, one playing back the full body, and the other, and then you can play back a different animation data on the 2 arms. And what we would like to do in the future is to add an interface, a GUI, for editing the MMS, because now the only way is to open the MMS with a software like Excel edit manually the numbers and watching the results. This is, of course, not user-friendly. We would like to have an interface using 3D gizmos in order to edit the signs in a faster and more reliable way. And also there is a thesis going on to improve the transition, because now the transition between signs is made using the default Blender interpolation routines, but we are working on machine learning methods to better match what will be the transition according to the physics of the body. So to have a more realistic bouncings and delays and reactions on the whole body. The idea for other projects is that the MMS is used as intermediate representation format for sign language, so that we will have systems translating from text into MMS, and then from MMS to animation. There is no need of a lot of data or deep learning methods, because the software is there and based on explicit imperative programming. But to train systems able to translate from text to MMS, we need indeed a user interface in order to start to create more content and provide enough content to a deep learning method to learn how to convert the text into MMS, which means glosses plus all the timing information plus all the inflection parameters. We have seminal work on this, but we will need more data to have a working system. Finally, I need to thank a lot Shailesh Mishra, who was a master student of mine and implemented most of the code of the MMS under my supervision. And yeah, that's it about the explanation of what is the MMS player, and we hope to find nice collaborations and people interested in using this software, testing it, reporting wishes for features and collaborations to get more funding to continue its development and eventually see it applied in real cases in the near future. Thanks, everybody.